now?
Okay, it's recording.
All right, perfect. Okay, so today I'm going to go through some of the Bayesian network construction methods that I used in my master's thesis work. Okay, so our question is, how do we use our data to construct a Bayesian network? So we have our conceptual model for Sacramento work, and we have lots of data. And so now we're at the point where how do we use that to construct our Bayesian network? And so this is a little background on Bayesian network. Probably everybody who's watching this will be familiar with it. But Bayesian networks are directed acyclic graphs that relate variables represented by nodes through conditional probabilities. So over here are a few nodes within a Bayesian network, and the relationship between the nodes are their parent nodes that influence child nodes in the network. And so the child node can then become a parent node for the nodes further down in the network. And so the way that we define these relationships between the nodes and how we quantify them is using conditional probability tables. And so this is a conditional probability table here on the right. And that takes every combination of the states from the parent nodes and has a probability distribution that defines what that relationship is probabilistically. And so on these nodes, there's these different lines here, and these are the different states. And so there can be continuous states like this one, which is chlorpyrifos concentration. And so this is a continuous variable that's broken up into intervals. And those are the different states. And on the right side is the probability of this node being in that state. So this is telling us that there's a 99.2% probability that the chlorpyrifos concentration is between 0 and 0.15. Okay. So for CPT construction methods, I'm going to go over some of the methods that I used while I was constructing the Bayesian network from my research. Those are case file learning. And that's when you use case files and use that to use a machine learning function that takes into account each data point to build a conditional probability table. And then the next one is equation to table function. And for this one, you can take an equation, this defining relationship, a dose response model, for example, take that equation and put it in Netica, and it will use that equation and randomly sample from that equation within the different states to create those conditional probabilities. The next method is peg the corners. And this one, you kind of take the information from the literature and different science or prior information that you have and set the probabilities for the most extreme conditions in your table, and then kind of interpolate what the states in the middle of those extreme states would be. I'll go over examples for that too. And then another thing that I did was using the prediction intervals from a linear model. And so this was a method that I used as an alternative to the equation to table function to try to better account for the variability within the prediction intervals. And then another great source for this topic is Marco et al. 2006. And there's a reference at the bottom of the slide, and that is a great starting point for how you develop and build these construction or conditional probability tables in Bayesian networks. So here's a conceptual model for my research, and this is a model that's taking into account pesticide concentrations and water quality variables and the impact to Chinook salmon through a toxicity pathway where the pesticides inhibit acetylcholinesterase, leading to lethal and non-lethal effects summarized in a toxic effects node. And then there's impacts to juvenile egg to emergence and adult Chinook salmon. And then the endpoint is Chinook population. So here's the Bayesian network for it. And so the examples that I'll start with are from the toxicity pathway because I use 3 different methods within this pathway. So for the chlorpyrifos concentration nodes, I construct the CPTs using the case file learning. And then for the toxicology effects, using the concentration response equations, using the equation to table function. And then for the summary node that summarizes toxicological effects, that was constructed using the peg the corners method. So this is the organophosphate pesticides nodes. And this is a map showing where the sample locations were. And so the first part of constructing your node is setting the discrete states. And so this can be done with a variety of methods. In this case, this chlorpyrifos concentration, I use the endangered species level of concern as the lowest category, or as the lowest limit. This is a concentration at which you would expect to see no effects to Chinook salmon, or very low effects at least. And then the other 2 are from Leitzel, which was the study where they were doing the toxicology tests, toxicity tests on coho salmon. And so this is 0.2 times the EC50, so 20% of the EC50 for the medium effects category, and then the EC50 for the high effects. And so that's just the way that I broke this up into different states. And so that will correspond with low and medium toxicological effects we would expect. Okay. So case file learning is very simple in practice when you use this method. So you need a spreadsheet that has all your data that you want to include. So this is a great method for when you have environmental sampling data and you have it in a spreadsheet. The main things is that you need a spreadsheet that has the parent nodes also included with your sampling results. So this is an example of a spreadsheet that would be ready to upload as the case file learning file. And so you have the season that corresponds to the season node, and these have to match exactly, and they're case sensitive. In order for the case file learning to work, it needs to match the node names for the parent nodes. And then, so this is the steps that you would do in Netica. You select the node, and then from the top toolbar, you select cases, learn, incorporate case file. You select the spreadsheet file, and then it'll ask you if you want to reset the probability table. So if there are already information in the conditional probability table and you're just adding to that, then you would say no. But if you just want to start fresh and then build the conditional probability table from the file that you're uploading, then you would say yes. And then enter degree, and 1 is the default. And so this is a way to kind of weight your data or your cases. So if you were to put 2, then it would basically count each data point twice, So if you put it counts it twice, it would influence the probabilities a lot more heavily. So when we've done this, we've always just used one, and it's the default. And then, yeah, it uses a counting algorithm where it'll go through and count each data point and adjust the probabilities for the different states based on if a data point falls within these two conditions of the parent nodes, then it will influence it. It will adjust the probabilities of where, if it landed between these two, for example, then it would increase the probability here, and the probabilities here would decrease. And so just step by step with each data point to take each one into account. And so that was conditional. So next, table 2, equation to table function. And so we'll use the acetylcholinesterase inhibition node as our example. And so this one is it's the inhibition of acetylcholinesterase activity caused by chlorpyrifos and diazinon as a binary mixture. And that's this graph here is showing the concentration response curve from the Lates et al. Data where they conducted the toxicology tests with these binary mixtures. And this is done with toxic units. That's how I calculated this curve. And toxic units are normalizing the concentration by the EC50. And so you have your x-axis is a measurement of toxicity in itself, since it's normalized by the EC50, and then you can add the toxic units together for different chemicals, and it's a proportional toxicity for those different chemicals. And so in order to put the equation into Netica, this is kind of an outline of how I went about that. So this was done in R using the DRC package. And when you construct the model with DRC, it will give you the equation, or it'll give you the parameters in the equation. You can fill it in here. So this is a log logistic 3-parameter model. And here's the equation for that with the parameters from this model put in, where X is the concentration. And so in Netica, this is the format where you would put it into Netica, and there's a box where you can put the equation in. And it's the same thing, except for, since we have our diazinon and chlorpyrifos nodes in micrograms per liter, we have to convert that into toxic units for this model to work. So within the equation to put into Netica, I put the equation here that calculates the toxic units within the model. So instead of this X from this part, there's just this part that calculates or converts it to toxic units within the equation. And so this is what it looks like in Netica. If you double click on a node, it will open up a properties box. And then in that part, you click on this part right here, and there's a drop-down menu, and you go down to equation, and you can put in the equation in this part. Click OK, and then you select the node again, and then at the toolbar at the top, you click on table, and then equation to table. And then that will use the equation in here to construct this conditional probability table. And it does that by random sampling within each state, or within each range here. It does a few random samples within that range, and then adjust the probability in a similar way to the case file learning. And so you can kind of see the dose response relationship within the table here. So here's the lowest concentrations, there's a high probability that the acetylcholinesterase is at 100% of the control group. And then as the concentrations increase, the probability increases that the acetylcholinesterase is more inhibited, with the most extreme cases down here where the two different chemicals are at their highest concentrations. And so, yeah, both of these functions are pretty easy to put in. Once you know what you're doing, the case file learning, or like what you do in Etica, is very easy. And okay, so peg the corners. With this approach, you kind of take a look at each combination of your input nodes. So this is taking the mortality effects and the change in swimming rate and putting these together, taking each case of each combination of these, and then estimating what the probability of, this is like 90%, these different states are percent of the percent probability that the fish is going to die. So this is 0 mortality, and this is 90% mortality. And so yeah, just kind of go with each of these extreme cases. So the 0% change in swimming speed and 10% mortality. This is the probability distribution, and these are very broad because this is more of an explanation, more of a estimation. So this is a very broad probability range, and that represents the uncertainty in doing this process. And so an important part to keep in mind with this kind of approach is that this is really a starting point in our knowledge of this. And so this plays into how Bayesian networks and Bayesian networks in the context of ecological risk assessment is an iterative process. So with the iterations of using this model, we would be able to adjust these probabilities to better fit what we actually see. That's an adaptive management type of thing as well. Okay, so next up is the prediction intervals from a linear model. And I sent Emma the code on this one, so you might be a little familiar with this one. But so in this part of the model, we're looking at the water temperature as a stressor. And in my research, I was looking at future climate projections as well as historical climate data. And so for the future climate projections, those are in air temperature. So I needed to relate that to water temperature in order to use it in the model. And so this relationship right here is defining what the probability of the water temperatures would be given these air temperature projections. And so the way that I had to define that and create a conditional probability table is I used environmental sampling data they were risk region and season specific. And they were sampling data that were sampling air temperature and water temperature at the same time. And so I created a linear regression with those data. And you can see there's a very large data set on this. So I wanted to use the prediction intervals to represent this uncertainty as a more accurate way than using the regression. And even if I tried to use the confidence intervals, those would be very tiny because of the large data set. So this is a graph where it has that same data with the prediction intervals. And then this is a grid with the discretization or the discrete states for the air temperature node on the x-axis and the water temperature node on the y-axis. And so this grid is showing how the different states overlap. And so what I'm interested in is the range of these states overlapping with the range of the prediction intervals. And to do that, and here's an illustration of what I mean here. So there's a range of the prediction intervals within this state. So we're looking at 0 to 10 degrees air temperature, trying to predict the probability of what the water temperature would be. We have this range of prediction intervals, and it's overlapping two states of the water temperature node. And so the way I calculated this was the proportion of this range being in part of this state, and this range, the proportion of this one to this range within the state. And so I wrote an R program script that could calculate that for each state, for each sampling set too. So this is for the risk region 1 during the summer, and then I have another one for each season for risk region 1, and then all the way through risk region 5. And so using this method, this is what the conditional probability table looks like. So the example we were looking at between these two states is the same as this one right here, 0 to 10 degrees. And so there's a 60.1% probability of here and a 40% probability of here. And so that's just the proportion of the overlap. And so it can kind of give you some ideas about how you can think about translating the different kind of data you have into conditional probabilities to put into your table when you're creating these relationships. Yeah, and those are the main ones that I used. I was constructing my Bayesian network.
Awesome. Do you want me to keep recording through the questions if we have any questions? I can.
Yeah, that might be helpful.
Okay.
People. All right. So ready for questions?
Thank you, Eric.
Yeah.
That was great.
Yeah.
Just to make sure that I understand you correctly, could you go back to the last figure that you were showing? So when you said that you were calculating the proportion of all observations, so given an interval of your X value, you were looking at the Y values and finding out how many samples fell into each of your Y bins and using that proportion as what you populate the table with?
Right. So this one is within this range. I need a probability distribution for the water temperature. And so the probability of the water temperature being in this state or in this state, or we can look at it here as it being in this state or is in this state. What's the probability that the water temperature is going to fall into those two states? And so the way I did that was I took this range right here. This is the part of the prediction interval that's within this state only.
Mm-hmm.
And then, so I took the full range subtracted by that, or no?
Cool.
The full range. I'm confusing myself, but I did a subtraction to see what the proportion of that is.
Yeah, maybe the total number of samples that fall within that bin minus the number of samples or that fall within that X bin minus the number of samples that fall within that X and the other Ys.
Right, but instead of number of samples, it's just the range. So it's
Oh,
just the range there. So it's just treating it like as if the number of samples is just uniform across the prediction interval, basically.
oh, interesting. Would you be able to share the making of this table, like if you still have them, the calculations that helped you do that?
Yeah,
Because it seems like a really helpful, especially with data that's going to be have a lot of variance and maybe not fit an equation very well. This seems like going to be a pretty common approach
yeah,
to use.
this was a fun one too. I spent a lot of time in our making
Yeah, I
functions and stuff.
believe it.
And yeah, what I wanted to do as well is, since this is very simplified because it's just working with lines, so
Hmm.
it's just kind of, you just take ranges and subtract. But I was thinking about if we wanted to do this with the prediction intervals for dose response equations, it would get a lot more complicated, and I'd have to break out my calculus textbook and try to remember all that stuff. And I was also thinking about using areas. So like maybe a better representation of this one here, instead of subtracting it, using the area within this and the area within this
Hmm.
as a proportional measure.
Yeah.
But yeah, just some different ideas for that. If I had a bunch of time and funding, maybe I could start writing some programs for that. That'd be fun.
That would be one of those things that's like, how much time am I going to commit to this? And I did have one other question. When you were showing your peg the corners example, um, so I know that we've talked in the past about how once you get over like three discrete states, it can get complicated. Was that something that Wayne and you had mentioned? And so I was just interested in the decision to use, um, the 5 different states for these, for the percent mortality and the toxicological effects.
Yeah, that's a good question. And the reason why these ones are split up that way is because these were used as input into the population model. And so, especially like the larger context. So those are the input parameters for the population model, is these different like levels going into that. So that's why there's 5 of them there. But,
Okay.
oh, went too far. Way too far. My computer's going a little slow right now.
No
Here.
worries.
Yeah, so you can see all these ones that are going as inputs into the population model. And so the population model was run separately to construct this conditional probability table. But this is, they all have that same kind of setup.
That makes sense. Did you run into any extra troubles dealing with those, or was it pretty smooth because those were so late in the Bayesian network?
So for me, luckily, I didn't have to do much with the population modeling, because that was already done by the time I started working on this project with Chelsea Mitchell at Washington State University, was collaborating with Valerie Chu, who was doing a very similar thing as this, as like she was working on this pathway as like including EOPs or AOPs within the Bayesian network. And then Chelsea Mitchell was doing the population modeling part of that. And so for me, I just kind of got to do the climate change stuff and also kind of updating the methods on this part as well. But from what I can tell, it was a very complicated process to do all the population modeling stuff. But when I was talking to Chelsea, she said it was, since it was her first time doing that, she made it more complicated than it needed to be.
That seems fair. Yeah, I can only imagine how complicated building one of those would be. Well, those were all my questions. Emma, did you have any?
I don't think I have any questions. No, I'm good. That was awesome, Eric. Really, really helpful.
And I know that it's also very helpful to walk through these things in Etika, like I did with Erica and Skylar the other day.
Yeah.
So as you all are working on these and constructing this stuff for yourself, and if anything is unclear, let me know, and then we can go through it in Etika. Makes things a lot easier.
That sounds fantastic. I'm very sure something will come up that I would love some support on. So thank you.
Yeah, absolutely. Thanks so much, Eric, for taking the time to put this together and share it with us.
Yeah, thank you.